All right, so let's start the class. Okay, so before we move to a different topic, I want to go back to the theorem from last time that I thought was slightly incomplete, and I want to give the proof again, which is that the space of C-infinity functions is Bayer. So let's do that again. Oh, and I should say that please don't write on the chat right now, or if you do, I won't see it. So if you want to say something, you can unmute yourself and say something, because I can't see you and I can't see the chat. All right. So the theorem I'm going to reprove is let X and Y be smooth manifolds, then the set of C-infinity functions is Bayer in the C-infinity topology. Okay, so I'm going to go kind of quickly because last time I already explained the proof, but there are a couple of places I think it's better to clarify. And one of them is I was taking closures of sets, and that's a little confusing because the closure changes when you change the topology. So the C-infinity topology is a union of topologies. And if you're open for one topology, so if you're open in CK, then you are open in C-infinity. But closed is the opposite. So for you to be closed in C-infinity, you have to be closed in every CK. For a sequence to converge in C-infinity, it has to converge in every CK. So that's why I think it's a little better to avoid taking closures of sets unless we're 100% sure of what we're talking about. I think someone wrote something on the chat. Could you say that, please? I can't see it.
Alguém pediu para aumentar a letra, eu acho.
Para aumentar a letra. Tá, eu vou tentar. Obrigado. Okay, so we start by fixing. So we fix complete metrics dk on each jet space. So we'll use that to look at the balls. Actually, that's the main thing I need to clarify. But let's go back to let's do the proof again. We're not in a big hurry. So remember what we have to show is we have to consider a countable collection of open sets. These are open and dense sets in C-infinity of xy, and we need to show that the intersection is dense. So we want to show that the intersection is dense. What does it mean to be dense? It means that it intersects every open set, every non-empty open set. So we take a V, an open set, which is non-empty, obviously. And we want to show that it will intersect this countable intersection. Okay. So the first thing is because it's an open set that's non-empty, we can find a smaller open set in there, and we can find a base for a basic element. So a basic element is a basic element of some K0 topology. So there exists what I'm going to call a Z, which is an open set in a jet space such that M of Z is contained in V. Okay, this is because M of Z's, these guys of this form a base for the CK topology, and the union of them forms a base for the C-infinity topology. Okay, so we can always find a set of this form that's inside there. But more than that, we can always shrink it a little bit, shrink Z a little bit, and make sure that M of Z bar is contained in V. And here's what I was trying to say earlier. Like if you take some subset of the jet space, then it's well defined what the closure is. It's because this is just a manifold, a finite dimensional manifold. And then we can look at M of Z bar. and this is the space of functions. Okay, so that it makes sense to talk about that. But if you looked at M of Z and you took the bar of that, it's a little bit more subtle because it depends on which topology you do that. Okay, so that's why I'm going to avoid doing that. And it's fine, you can do that. So, basically, if you look at MZ bar and you look in the CK topology, then that's, M of Z bar. But, that's why if you look at the same infinity topology, this set is going to be, in general, smaller than this set because you have to have all the derivatives converge, basically. Okay. So, yeah. So we can choose such a Z. Okay. So, of course, it's enough to show that M of Z bar intersects this guy. Okay, so we're going to find a function which is in M of Z bar and also in all of the UIs. Okay, so just, what I said last time is we construct a sequence. So we can construct Fi inductively. So it satisfies three properties. I'm gonna write it like this. So first of all, we're gonna construct sets Fi, and we're also gonna construct something that's smaller than UI, but whose closure, basically this M of the closure, is gonna be in UI as well. So we're gonna construct this and also a sequence Ki, a sequence of natural numbers, and a sequence of Zi's, which are going to be in the Ki jet space, open sets, such that, so first of all, F is going to be in M of Fi is going to be in M of Z intersection with basically the M of Z S for S equals 1 until I. Okay, so, and then what's the significance of Zi? The significance is that M of Zi bar is in UI. And then the third thing is that these Fi's are going to be like a Cauchy sequence, but they're going to be a Cauchy sequence in every, with respect to, basically in every jet space, for every point X, we're going to have a Cauchy sequence. So the condition that I want, and this is where I kind of wasn't very careful last time, is I want the kth distance of the jet space, I want ds of Js of Fi of X. So the distance of the S jet of Fi and Fi minus 1 of X, I want this to be less than 1 over 2 to the I for every X in X and for every S between 0 and I. Okay, so I want to require that all the jets, the distance between all the jets in the given metric is sufficiently small. Okay, so this is the condition, like last time, I think I just said the di of this is less than 1 over 2i, and there was some confusion about how you get an actual Cauchy sequence for a given metric space. Okay, so this is the condition, these are the conditions that we want, and how do we build such Fs? Basically what I already said, but let me quickly do it again. So, first of all, since you start with U1, so so U1 is open and dense, so when you intersect it with M of Z, you have that this is open and non-empty. Because you're using the fact that UI is open and dense. Okay, so it's open and non-empty, so we can find an open set in there, in particular. So we can find a non-empty open set. So we can choose, or we can find what I'm going to call Z1, which is inside of some jet space for some K1, such that M of Z1 is contained in M of Z intersected with U1. And actually, again, I can choose it small enough so that M of Z1 bar, so if I can find Z1, I can always find something smaller whose closure is in there. Okay? So then I can just take F1 to be some point of M of Z1. So, I can find the Z1, of course, non-empty. Okay? So you see that F1 is going to satisfy this. So F1 is F1 is in M of Z intersected with M of Z1. And so I have property 1 and property 2. I know that M of Z1 bar, it's contained in this intersection, so it's contained in U1. Okay, so F1, you just choose like this. And now for the induction step, so say that we have already chosen Fi minus 1. So say we've chosen Fi minus 1, and then the and all the ki minus 1. I mean, say you've chosen these guys for chosen Fs, Ks, and Zs for s less than or equal to I minus 1. Okay, so how do you choose these guys for s equals 1? So, it's kind of the same thing, but it's a little more complicated. And now we have the third condition coming in. So we define, I'm going to define the set di, which is now it's going to be these balls. So it's going to be the ball of radius 1 over 2 to the I, but in the topology, in the C0 topology, centered at Fi minus 1. Then I intersect that with the ball in the C1 topology of the same radius, centered at F1 I minus 1, and so on until Bi of 1 over 2 to the I of Fi minus 1. Okay, so I do these intersections, and I mean, clearly, I have that a function is in di if and only if this condition is satisfied for these jets. Okay, so the point is that this di is open in the Ci topology, and in particular in the C infinity topology. Okay, so now I can look at M of Z intersection with M of Z1 intersection with M of Z I minus 1. So these guys are all defined. And then I take the intersection with DI. So, by the induction hypothesis, these are all open. So when I take the intersection with the and non-empty, so when I take the intersection with the I, this is also going to be open and non-empty because Fi minus 1 is clearly in there. So this is open, and this is a finite intersection of open sets, and it's non-empty because Fi minus 1 is in there. So then it's going to have to intersect Ui. So recall, Ui is open and dense. So when I intersect Ui, I'm going to have an open and non-empty set. So when I look at this guy, MZ1, etc., MZI minus 1, intersection with DI, intersection with UI, this has to be non-empty and open. So then I can find a ZI inside of some KI jet space such that M of Zi bar is contained in this intersection. So again, of course, non-empty. So it's contained in this intersection. Intersection with DI, intersection with UI. Okay, and then again, now I choose some function fi, which is in M of Zi, just M of Zi. Okay, and then you see that I will have those three properties. So, clearly, now if I'm in M of Zi, then I'm going to be, I will have the property that fi is in M of Z intersection with all these M's of Z S from S equals 1 to I. I have the second property, which is that M of Zi bar is contained in UI. And finally, I have the property that Fi belongs to Di. That's the same as saying that the distance of the jets, the S jet of Fi, that Fi is in the S ball of radius blah blah blah. So that's the same as saying that. Sorry, let me write it. This is the same as saying that Fi is in the ball S of radius 1 over 2I, centered at F I minus 1 for every S less than or equal to I. Okay. So this is what it is. Okay, so that's the condition that I wanted before. Okay, so now, is it clear? Are there any questions? Okay, so now I can use this second. So I've constructed this inductively. I've constructed a sequence like that of Fi's and Zi's and the K's, which we don't really care very much about the Ki. So then the condition, the third condition is saying that the S of the S jet of Fi at X, the distance between this and Fi minus 1 of X is less than 1 over 2 to the I for every X and for S between 0 and I. So that means that for a fixed S, when you look at the JS of Fi of X, this is a Cauchy sequence. Cauchy sequence in the jet space JS of XY. Okay? So since we chose a complete metric, that means that this JS of Fi up to a subsequence is going to converge to some JS of X. It converges in this manifold, so in any metric topology. So this is a finite dimensional manifold. So this converges for every point X. Okay. So if you look, you can look at G0, which G0 of X is something that's in the zero jet of XY, which is the same as X times Y. And this is basically, because it's a section, this is basically given as X and then some function of X. You can call it G of X. Actually, this is my definition of G. Okay. So now the exercise, and now this is really an exercise. It's not very hard, but it's to show that this G is a smooth function and that the S jet of G is just as GS. So how do you do that? You basically just look in charts and you see that, you fix a compact set and you look in charts and you see that the convergence here, in the jet space, it gives rise to a uniform convergence, a uniform CS convergence on this fixed compact set. And you use a little bit of analysis to show that this G has to be smooth and that they have to be the derivatives of G have to be seen by the other functions. It's not completely obvious, but it's an analysis exercise. So you have to look in a compact set and in charts. If you want, using that description of the CK topology that I gave you last time. Or, kind of just go directly here using this metric. Okay. So once you have that, then basically, this G is, this G is the limit of Fi in the C-infinity topology. Because, it will be the limit in the CK topology for every K. So it means that the Fi do converge to G with all the derivatives. Okay, and then now, since the Fi was in M of Z for every I, then the limit G, it has to be in M of Z bar. Okay, I mean, and this, is kind of truncated, like you only care up to a certain K. You just care about the convergence in CK0, where K0 is the jet space where Z belongs. Okay, and then similarly, we have that Fi belongs to M of ZS for I bigger than or equal to S. Okay, that's because, condition number one, let me go back here. Fi is not only in Zi, but it's in all the ZS's for I bigger than or equal to S. So this implies that the limit is going to be in M of ZS bar for every S. So the conclusion is that G is in M of Z bar intersected with the intersection of all of the M of ZS's for S equals 1 to infinity. And, by the way, we chose Z bar, this is going to be in V intersected the intersection of all U. I'm going to change my index, UI. Okay, so therefore this guy is non-empty. So this is non-empty. Okay, this is it. That's a cleaner proof. Okay, any questions about this? All right, are you guys there?
Yes.
Okay, all right. Okay, so now we're going to move into the transversality theorems. So now that we've established this first result, now we're going to get a little more concrete and talk about the stuff that we really care about, which is like using this machinery to talk about transversality. So this is topic 4. Transversality theorems. Okay, so here's the definition of transversality. So let X and Y be manifolds, and let F be a smooth function. And let W be a submanifold of Y, of the target. So we say that F is transverse to W, and we write like this: F is transverse to W if for every X in the preimage of W, we have the following condition. When you look at the tangent space of X and you push it forward by df, and then you look at the tangent space of W at f of X, if those together span the whole tangent space of Y at f of X. Okay, so this is a generalization of the maybe more well-known idea of transversality of two submanifolds. So note that if X1 and X2 are submanifolds of Y, usually, we say that X1 is intersects X2 transversely. They intersect each other transversely if, or let me say, if and only if. So what does that mean? That means that the tangent space of X1 plus the tangent space of X2 at the same point, at a point of intersection, is equal to the tangent space of Y whenever, for every X in the intersection of X1 and X2. So this is the notion that's maybe even more well known. But this notion of a function intersecting a submanifold of the target is more general, but it's actually easier to use and to prove theorems with. And the second notion here, which is maybe the more traditional notion, is just a consequence of this. So this is, you can obtain the second condition just using the inclusion. So you can think of the inclusion of X1 into Y, and it's easy to see that X1 intersects X2 transversely if and only if the inclusion of X1 is transverse to X2. Okay? And you'll see that, it's a lot easier to prove theorems about this. And the reason is because a lot of times we want to perturb. So, if you're thinking about two manifolds intersecting transversely, you're like, well, it's not transverse, and you want to perturb. What does it mean to perturb a submanifold? It's a lot harder to talk about that than it is to talk about perturbing functions. So that's why we're going to concentrate our, efforts on this kind of thing. And in manifolds that intersect transversely, that's a subcase of the general transversality definition. Okay? Any questions about this? Okay, so maybe some examples. Let's start with. So I guess the first example is, let's say you have a function from R to R, and let's call, so what does it mean for, well, let's say that F is the graph of F, which is a map from R to R2, that takes X to f of X, also known as the zero jet of F, if you want. So when does the graph or the zero jet intersect R times 0, the x-axis transversely? Okay, so this happens if and only if. Okay, I guess we can write down what it means. So it means that your df x of your tangent space of R plus the tangent space of r times 0, if this generates if x, I should say, x0 of r times 0, if this generates the space, the whole tangent space of R2. So, let's just draw the picture. So I have a function, and you have the graph, and you look at the points where the graph of f intersects the 0 axis. So, these points here. And what you're looking is, so you look at the derivative of the function. So basically, it's this tangent space here. That's the first one. And then the second one is this tangent space here. So it's always the tangent space of r times 0. And you want to make sure these two span the whole tangent space. For every time that x is a 0 of the function. So, if you look at this condition, this says that f intersects r times 0 if and only if basically you don't have a 0 of the function and derivative of the same time. So if f, provided that f is smooth, or at least C1. Actually, we're talking just about smooth functions. So this is if and only if the intersection of the preimage of 0 and the preimage of 0 of the derivative is empty. Okay, so these are all transverse. So a situation that's not transverse is when you have the derivative and the function vanishing at the same point. So that's not a transverse situation. And the main idea of transversality, which we're going to kind of talk about in different ways, is that every time you have a situation that's not transverse, if you perturb it, it'll become transverse. So you see that in this case, if you perturb it in whatever way you want, if you think about perturbing the function, this infinity topology, and which is or perturbing this capital F in this infinity topology, which is basically the same thing, then you're going to get you either get this or you get this, and both situations are transverse. Okay. Any questions about this? Okay, here's another nice example. So say they have a function from R to R3. And say that W is a curve. I mean, you can think of this as just like two curves, but I want to think of one curve as a submanifold and one curve as the image of a function. Okay. So now, how can you get... Oi.
Desculpa, eu me perdi
Fala.
pouco. Quando não se intersectam, a gente vai dizer que também é transversal?
Sim, exactly. So that's because of the definition. So it's like vacuous definition. So the condition is for every point in the intersection, something holds, right? So if there are no point in the intersection, then the condition holds.
Sim.
Yeah. So that's this is exactly the point of number 2. So if you have two curves, and if they do intersect, like if they do intersect, and you're in 3-dimensional space, then, or if you think about the image of a curve, of course the first the derivative of f, the image is 1-dimensional. It's at most 1-dimensional. So if they do intersect, then they cannot be transverse. So if you have something like this, then they can only be transverse. So that they are transverse if and only if the image of f does not intersect W. Okay? So in fact, we can just put this together in a little proposition. So let X and Y be manifolds. and let f be a smooth function, and y be a submanifold of the domain, such that the dimension of x plus the dimension of w is strictly less than the dimension of y. Then f intersects omega transversely if and only if the image of f doesn't intersect w. Okay, so if we have this dimension condition, then there is no way that being transversely having a transverse intersection means that they don't intersect. Okay, so what's the proof? The proof is very simple. So
Profe,
Vamos.
hello, sorry, I think my connection got lost. Let's continue here. So, yeah, I was saying that, can you hear me? Just to make sure.
Sim,
Sim,
mas
ok.
não dá pra ver a tela.
Ah, não dá para ver a tela. Ah, sim, eu não compartilhei ainda. De novo. Obrigado. Ok. Now you can see the screen. Dá para ver agora?
Sim,
Okay. All right. So I was saying that, suppose that you have, you take a point on the image of f that is in W, okay? And suppose we have this condition here. Then when you look at df of x of txx plus, so when you look at the space that this guy generates with W, the dimension of that, the biggest that this can be is the sum of these two. So if they only intersect at 0, then you have the dimension of this guy plus the dimension of this guy. And the dimension of the image of a function is at most the dimension of the space itself. So the dimension of this span here is at most the dimension of x plus the dimension of w. And if this is strictly less than the dimension of y, which is the dimension of t of f of x of y, then there is no way that the span here can be equal to this tangent space at y. So F is not transverse at y, and I'm going to write it like this. Not. Because I don't want to write another dash on top of the transverse. Okay. F is not transverse to W. So here I proved the contrapositive of the only direction that's relevant here. So if the intersection is not empty, then F cannot be transverse to W. Okay. And it's obvious that if the intersection is empty, then F is transverse to W just by definition. Okay? Any questions about this? No. Okay, so let's keep going. All right, so now we have a very nice theorem, which is not very hard, but it's very, very important, which is what happens when you take the pre-image, when F is transverse to W, what happens when you take the pre-image of W? So again, let's X and Y be manifolds, F a smooth function from X to Y, and W a submanifold of Y, such that F is transverse to W. And suppose, so if F inverse of W is non-empty, then it is a submanifold of X of codimension equal to the codimension of W. Okay? Codimension just means the complement of the dimension. So this means that the dimension of X minus the dimension of the pre-image is equal to the dimension of Y minus the dimension of W. So this is just an easier formula to remember. So, this means that the dimension of this pre-image is equal to the dimension of X minus the dimension of Y plus the dimension of W. Okay, so, maybe this formula, you're going to mess up the signs. It's much easier to remember that when you take the pre-image of a submanifold, if it's transverse, then it will be a submanifold and the codimension is the same. Okay, so let me actually just write it like this. Okay, so this is the same. Okay, any questions about this? About the statement of the theorem? This is a generalization of the theorem that we proved before that was basically just the implicit function theorem, which said that if you have a regular value, then the pre-image of the regular value is a submanifold of codimension given by the dimension of the target. And in fact, you see that that's all we need to prove this theorem anyway. So they're equivalent. But this one, is a lot more general to apply, in lots of circumstances. Okay, so here is the proof. No questions about the theorem? All right. Oh, and see that, for this to make sense, we need that the dimension of X plus the dimension of Y is bigger than or equal to the dimension. Sorry, the dimension of X plus the dimension of W is bigger than or equal to the dimension of Y. Otherwise, this number here is less than 0. Okay. Oh, and I should also say that in particular, a case that is very often used, if the dimension of X is equal to the codimension of W, then F inverse of W consists of isolated points. So it's an embedded zero-dimensional manifold. So it has to be a bunch of isolated points. Okay, so that this condition here just means that this number will be equal to 0. Okay, so this is a case that we're going to use a lot in this course for the intersection theory part. Okay, so now let's prove the theorem. And as I already kind of told you a few minutes ago, the idea is to turn this problem into, to turn this condition, this transversality condition, into a condition of regular values. And then to show that this is basically the preimage of a regular value of another function. And then we'll be basically done. So the first thing we do is look at this in charts. So let's take a point which is in the preimage of W. And so we stop writing dimensions. Let's just say that n is the dimension of x, m is the dimension of y, and k is the dimension of W. Okay? So now I can fix a chart near P. So let phi going from U to R N be a chart. Oh no, sorry, I want a chart around F of P. So let this be a chart around F of P such that when you look at the such that W, so we know that W is a submanifold, so we can choose a chart near this in the neighborhood of a point on the submanifold such that the submanifold is just the image of the submanifold is just a linear subspace. So we can, so phi of U intersected with W is just contained in R to the K times 0. Okay, so, and also, phi inverse of R to the K times 0 is U intersect to W. So we can pick a chart like this. Okay, so this is your chart. Like your submanifold can be seen in this chart as just a subspace, a vector subspace in Rn. And of course, we can assume that phi of P is 0. Okay, so now let me save some space. Put it up here. So now we can project from Rm into R m minus k. So let this be the orthogonal projection. So the orthogonal projection to Rk times 0, or I guess along Rk times 0. So that, that basically will mean that the kernel of this pi is exactly this Rk times 0. Okay? And I'm going to write phi like this with kind of a different way. This phi like this is going to be the composition of pi with this var phi. Okay, so this phi is basically the composition of the projection with the chart. So this phi here is now going to go from U into R n minus k. And this is a submersion. It's a submersion because phi is the diffeomorphism to the image. So it's an embedding, and pi is just a projection. So clearly that when you compose, you get a submersion. Okay, and the pre-image of 0. This is going to be exactly. Oops. W intersected with U. Okay, so this is because of this condition here. So when you take the pre-image of 0, as I told you, you get the whole RK times 0. That's the kernel of pi. And then by this condition here, you get just W. Okay, so now basically what I'm doing is I'm looking at W now as a 0 set of a submersion. And then now I can take the pre-image of W. So I'm going to make the following claim, and we're going to prove it. So the claim is that F is transverse to W at P if and only if P is a regular value of phi composed with F. So what I'm saying is that if I compose F with this function phi, then the transversality condition is just the condition of being a regular value at a specific point. Okay, so let's see why that's the case. So first of all, since the pre-image since W inside of U, taking the intersection of U is just looking locally, so basically just W. So W is just the pre-image of 0 by this phi, and 0 is a regular value because phi is a submersion. Then the kernel of d phi is the tangent space of W. So this is for every p that is in it, such that f of p is in W. Okay, that's follows directly from kind of the definition. Okay, so now we can write down the transversality assumption. So the transversality assumption. So suppose that your transversality assumption is that dfp of tpx plus t of f of p w is tfp of y, which is the same, U is an open set, so this is the same as the tangent space of U. Okay? And then now we can compose this with d phi of f of p. Okay, so now we can apply this, we can compose with d phi of f of p, and then what do we get? So on this side, we get d phi composed with f at the point p of tpx. And then here you get 0, right? Because because the tangent space of W is in the kernel of d phi, so here you get plus 0, so plus nothing, is equal to d phi of f of p of t f of p of U. But phi is a submersion, so that gives you the whole space. So this gives you all of our, I guess, the tangent space at the point 0 of r n minus k. Okay. Actually, it's not hard to see you can go back. So I guess going back, I should say it's an exercise, but very simple exercise. So the transversality assumption for P is equivalent to the fact that this guy here, the derivative here is surjective. Okay, so sorry, regular value and a regular point. Okay, so there we go. So this means, that F is transverse to W, at least on this open set U, if and only if phi, if and only if 0 is a regular value of phi composed with F. Okay, so yeah, but we are assuming that F is transverse to W everywhere, so in particular in this open set. So then 0 will be a regular value of this. So now we can use the implicit function theorem. So and recall that this is a function that goes from x into R. Well, it goes from not all of x, just a subset of x, but some u tilde on x. I guess I can call this F inverse of u into R m minus k. So it goes from some open set of x into Rm minus k. So by the implicit function theorem, we have that the pre-image of 0 is a submanifold. And this is the same as the pre-image of U intersected W. That's kind of, it's just because the pre-image of 0 of phi is U, is W in this little u. So this, by the implicit function theorem, this is a submanifold of, this open set. And the dimension has to be, of the codimension has to be the same as the codimension, as the dimension of this, of codimension m minus k. Okay, the codimension of the submanifold has to be the same as the dimension of the target. That's the implicit function theorem. Okay? So, because we do that locally, then that means the whole, so this is local, but so, if we can look at globally at the pre-image of all of W, so this is a submanifold of X of codimension m minus k, which is the codimension of W, which is the codimension of W. So that's it. That's the end. Okay. Any questions about this? So one more time, the idea is when you're looking at a function which is transverse to a submanifold, you look at the submanifold, you look at a chart where the submanifold is just a linear space, and then you project along that linear space, so that being on this linear space is the same as projecting to 0. And then when you compose the chart with the projection, you get a submersion. And you take this submersion and you project with the original function. So then you prove that the function is transverse to the submanifold if and only if 0 is a regular value of this composition. And then you just apply the implicit function theorem. Okay. Any questions? Okay, so let's continue. So now we're going to go into, in preparation for the general transversality theorem that we want, we're going to prove some results about jets. So the first one is the simplest one, but I think it's still kind of nice. So let X and Y be manifolds, and let W be a closed, or be a submanifold, which is a closed space. Submanifold, which is a closed subset. And I just want to say this because usually when people say use the word closed with manifold, they don't mean a closed subset. So I want to emphasize it's a closed subset of Y, but it's not a closed manifold, meaning it's not compact. So usually when people say a closed manifold, they mean that the manifold has no boundary and it's compact. But in this case, the result is true that I'm about to state, even for non-compact submanifolds. They just have to be closed subsets. Okay. Then I can define a set TW, which is the set of functions which are transverse to W. And the proposition is that this is open. In the C-infinity topology. Okay. So now let's prove this. I mean, I guess this is probably not very surprising if you understand what transversality is. So basically, this is saying if you have a transverse situation, then you can wiggle it around and it'll stay transverse. But there's this technical condition which you'll see where it comes up, which is that the manifold is a closed subset. Okay, so the proof. So we show that TW is open in the C1 topology. So actually, you just need one derivative. You don't even need infinitely many. Okay, so it's open in the C1 topology, and therefore it's open everywhere. So we're going to just see TW as M of something. So let U be the set of jets, so the set of one jets of functions. So I'm going to write it like this. I could have written the equivalence class of F, but let's just write it like this. So in J1 of xy, such that either f of x does not belong to W, or the transversality condition holds. Okay, so the claim, this is not the claim. So it's easy to see that TW is just M of U. So, it's the set of functions in C-infinity such that the one jet of F, the image of the one jet of F is contained in U. So for every point of X, either this transversality condition is satisfied or you're not in W. Okay, so what we need to show is that the claim is that U is open. Yeah, well, it's a subset of the one jet space. So of course, it's in the topology of the one jet space. Okay, so how do we show that the set is open? Well, you can show that the complement is closed. So we will show that V, which is the complement, so it's the one jet space, minus U is closed. Okay, so how do we show that? Let's take a sequence. I mean, this is a metric space, so it's a very easy to talk about, talk about things being closed. So it's sequentially, we can use a sequence. So to prove that, let's take a sequence inside of V, which converges in the jet space, such that sigma n converges to sigma in the jet space. So we need to show that the limit is in V. We need to show that sigma is in V. But first of all remember the functions alpha and beta. So beta, now we're going to use beta. Beta is a function that goes from the jet space to y. It just gives you the target. So if I'm in V, then if I have a so if I have a jet here, and so say that B of sigma n, beta of sigma n, so beta is a continuous function, so this has to converge to beta of sigma. But sigma n is in V, so that means that f of x is in W. So that means that, this has to be in W. So what does it mean for a jet to be in V? It means that the f of x, so beta of sigma n, has to be in W, and the transisality condition is not satisfied. So I have to have both things. So first of all, I am in beta of sigma n is in W, and because W is closed, then beta of sigma is also in W. Okay, so this is because the W is closed. Okay, so that's the first thing. So the limiting jet, the sigma, or you can write sigma is the J1 of some f, and f of x is in W. Now we have to look at the transisality condition. Then that's a little less subtle, but let's look at that in charts. So we have to see that if you take a sequence of jets where the transisality condition doesn't hold, then in the limit it still doesn't hold. Okay. So let's take charts around. So now choose charts around x and f of x. So this is alpha of sigma and beta of sigma if you want. So I'm going to choose the charts phi from not u. I don't know. Let's call this u tilde to Rn, and psi from v tilde to Rm. I just can't get away from the letters u and v as the domains of the chart, even if I used u and v for something else now. So let's put a tilde to differentiate them. So these two charts, and we have the submanifold. We can assume that psi of v tilde intersected with w is Rk times 0. So again, k is the dimension of w. Okay, and again, I'm also going to assume that phi of x is 0, and psi of f of x is 0. So they're centered at 0. And just to simplify, you can always do that. You can assume the charts are surjective, really, to have an equality here. But anyway, so now by what we said earlier, so F is so F is transverse to W at X. This is not by what we said earlier, but this is obvious that we can look at this in terms of charts. So this is if and only if psi composed with F composed with phi inverse is transverse to RK times 0 at 0. Okay, so I'm just changing the condition, the transversality condition. I'm looking in charts. And then I can use my projection. So this is if and only if, and by the same argument as from the previous proposition, if and only if 0 is a regular value of pi composed with this function. A regular point. Where pi is just the projection that goes from Rm into Rm minus k. So orthogonal projection. And this, and now is the point that's interesting. So, and then this happens if and only if 0 is a regular point of this, if and only if, when I look at the derivative, that has maximum rank. So if and only if pi composed with d of this guy at the point 0, if this has rank, maximum rank, which is m minus k. Okay, so now I'm going to look at the set of derivatives of that rank, or of stricter, of rank that's less than that. So now I can write F be the set of homomorphisms from Rn to Rm minus k, such that the rank of A is strictly less than m minus k. And now, in a neighborhood n of my jet sigma, if I fix phi and c, then we get a map that goes from the jet space into these homomorphisms. And the map is exactly given by this. So if I look at the sort of one jet of some function g at the point x, I just look at this guy. So I look at pi composed with d of psi composed with f composed with phi inverse of phi of x. Okay, so you basically just look at what happens to the derivative of f after you project using this orthogonal projection. And it's pretty easy to see that because of this condition here, that the transversality condition is equivalent to this derivative having rank m minus k. That's true not only at 0, but it's true also for every point. So, you have to look at this condition here, and you have to change the function and change the point, but it's exactly the same condition. So basically, when you look at the pre-image of f, that's the same as, So when you look at what v is, so v, at least in this n, that's the same as the pre-image of f. So basically, you have rank that's not maximum, if and only if, so the image of this guy has rank that's not maximum, if and only if the original jet was degenerate in this sense. So it didn't satisfy the transversality condition. Okay? And it's pretty easy to see that this eta is a continuous function. So all we need to show, and this N is an open set. So to prove that V is a closed set, all we need to show is that F is closed. So basically, we translate this problem of trying to look at the space in the subspace of the jet space, and wanted to see it's closed, to a linear algebra problem. So wanted to see that this F, this space F of matrices, which have rank that's less than m minus k, is a closed set. And that's a simple linear algebra problem. So I can leave that as an exercise. So I guess the exercise is that F is closed. Okay. So I mean, I can even tell you what it is. I just don't want to write it down. But if you take the matrices with a fixed rank, and the rank is less than m minus k, that's a no. Yeah, basically, if you take a sequence of matrices, you can only, and if they converge, you can only lower the rank. You can't increase the rank. That's yeah, but that's a simple exercise. And that's the end, because then we're showing that this V is closed, and therefore the U was open, and therefore TW, it was open in the C1 topology. Okay, let me just remind you what we were trying to prove. Maybe you already forgot. This is the proposition here. That the set of functions that are transverse to a submanifold, if they assume the submanifold is closed, that this is an open set. Okay, so it's really not very hard. It's just, you just have to go through the steps. Okay, any questions? Okay, so here's a remark. The condition that W is closed is necessary. So for example, if I take a circle, and then I take another submanifold, which is, say, a line, but open here. And say this is my W, and this is my F. Okay, so, I mean, this is the image of a circle. So this is in R3. Okay, so notice that F intersects W transversely because they don't intersect. But I can perturb F a little bit so that they do intersect. So if I perturb it a little bit, I can actually intersect this guy. And because they intersect, this is not a transverse intersection. Not transverse. In R3. Okay, so this is a simple counterexample. Any questions? Okay, so now we're getting to kind of gearing up to the main theorem, which we'll prove tomorrow, which is that the set of functions that are transverse to a given submanifold, or whose jets are transverse to a given submanifold, is a residual subset of C infinity, and therefore it's dense. But I'll state the theorem in a little bit. But before, let me prove a lemma that will be necessary. Well, yeah, no, let me do the lemma first. Maybe the lemma will seem a little dry, but it's also not very hard, so I guess it's okay. So let's fix manifolds X, Y, and B manifolds, and let's take Y, W a submanifold of Y, so this is the usual setup, and we're gonna let J be a map from B to the set of C-infinity functions. This is a map which is not necessarily continuous. And using this map, we can put together a function from X to Y. So this B is, you should think of this as like, I want to perturb my function. So I want kind of I want to look at a family of functions from X to Y. So I can think of that as a function from an index set B into this set of smooth manifolds. So you can think of this as like this. So it's a map of X times B into Y. Okay, so the map is given by J of B applied to X. So now we suppose that phi is smooth and that phi is transverse to W. Okay, so we make an assumption that the whole family phi is transverse to W. So the conclusion now is that for almost every B, or that the set of B's, it's not for almost because it's not measure theory, but that the set of B's such that the map with parameter B is transverse to W is dense. So let me write this down. Then the set of B's, the set of parameters such that J of B is transverse to W is dense in B. Okay. I mean, it's actually also full measure, but yeah, but this is going to come from Sard's theorem, as you'll see. Okay, any questions about this lemma? So let me say again what this lemma is saying. So if you have a family of maps from X to Y, a family that is indexed by some manifold, basically by some manifold B, if the family is seen as a map from X times B into Y, this family is smooth and is transverse to some Y, to some W, some manifold, then for almost every B, this J of B intersects W transversely. I mean, I just stated that it was dense. Okay, it's actually true for almost every B. Or it's actually true that it's even full measure. Okay. All right, so let's look at the proof. So, you know, we have a smooth map that's transverse to a submanifold. So I guess the first thing we do is we take the pre-image of the submanifold, and that's a submanifold of the domain. So we let W phi, this is the pre-image of W by phi, this is a submanifold of X times B. And then now I let PR be my projection onto B. And I'm going to let pi be the projection restricted to this W phi. So we claim that, I guess let me write this down. The claim is that B is a regular value of pi. If B is a regular value of pi, then J of B is transverse to W. Okay? So, you know, if Now, if you believe this claim, then we're done, because you know by Sartre's theorem that the set of regular values is full measure. So the set of critical values has measure 0. So in particular, the set of regular values is dense. Okay, and therefore, you know, this set that's bigger than this. So if this one is the set of these guys is dense, then this one is dense too. Okay, so now we have to prove the claim. So proof of the claim. So suppose B is a regular value of pi. Regular value of pi. We have to consider a few cases. So first of all, B could be a regular value because it's not in the image. So if B is not in the image of pi, then B is not a regular value of pi. That's fair. But if B is not in the image, then that means that there doesn't exist an x in X such that phi of xb is in W. Okay, so that means that JB of X doesn't intersect W. So, you know, so W doesn't intersect the image of J of B. So, you know, then that means that they're, so that means that they intersect transversely. The intersection, the transversality condition is vacuous. Okay, so if you're not in the image of B. Okay. All right, so that's the first case. Well, the second case is, so what if the dimension of W phi is strictly less than the dimension of B? Then, if B is a regular value of pi, then, you know, it has to be full rank, and the dimension has to be the dimension of B, but it's impossible, the dimension of the image of the derivative. So that means that B can't be in the image of phi. So then, so B can't be in the image of pi. And therefore, by one, we have the transversality condition. So really, the case that's interesting that we need to show is if the dimension of W phi is bigger than or equal to the dimension of B. And yeah, so that's really the condition that we want. And then now again, you know, if we take a point that, yeah, and now we take B that's a regular value. So let B be a regular value of pi, and let X be a point in X. So, you know, kind of again, it seems like I'm repeating myself, but, you know, these are little conditions that we have to consider. So if XB is not in W phi, then again, J of B of X is not in W, so J of B is transverse to W at the point X. Okay, so that's the easy case when XB is not in W phi. But now, of course, the real thing is if we get something in, if XB is in W phi, so if you take B a regular value and you take X anything such that XB is in W phi. Okay, so that means, you know, this is the pre-image. So that means if xb. So finally, I'm considering the case that matters, or the case that's interesting, which is that the pre-image of regular value. Okay, so you obtain the following thing. So we know that b is a regular value of the projection. So that means that t xb, when you look at the projection of this guy, that's going to be the whole tx of b, tb of b, because b is a regular value. So that means that you can actually you can look back, and the tangent space of the product has to be given by the tangent space of w phi at xb plus, now I just have to add everything in x. So these two tangent spaces have to span the tangent space of the product. I mean, it's possible that there's a bunch of overlap here, but basically, if this is not true, then this condition above cannot hold, because the second tangent space is taken to 0 by the projection. Okay, so this, let me just say, this is because b is a regular value of the projection. So remember that pi is just the projection restricted to omega phi. Okay, so now I can apply the derivative of phi. So now I can apply d phi at xb. So when I apply d phi of xb, what I have is I just have the tangent space of y at the point phi of xb, which is the same as j of b of x. So this is equal to this guy here, this tangent space of the pre-image gets mapped to the tangent space of w. Again, at the point, j of b at x, so, which is the same as phi of xb. And then, now, I just have this guy applied to this section, but this is the same as if I just look at d of x, this, I can look at the inclusion of x inside of x times b, the composition with this, and this is just going to be the differential of j of b at the point x. And this is the transversality condition for j of b. So j of b is transverse to w at x. Okay? So let me go back. Maybe it's not so easy to follow because, I don't have that much space to write. I don't have the whole blackboard in front of me. But yeah, so here, let me say it one more time what the lemma was. So again, if you have a family of functions that's parametrized by some manifold b, such that this kind of parametrization is a smooth function, and that is transverse to a submanifold of the target, then the set of parameters such that the function with that parameter is transverse to w is dense. And the proof was to show that basically you look at this manifold, this w phi, and you look at the projection, and in that b, if you have a regular value of the projection, then you have the transversality condition that you want. Okay? So this is kind of a technical lemma. It's not very hard. It's not very interesting, but it's going to be very useful in the proof of the Thom transversality theorem. So that's why I stated it now. And a corollary of this is that you can do the same thing for higher jets. So let G, so if you have a smooth family of functions, then you can let phi be the function that goes to the jet space, the kth jet of JB. So if phi is transverse to W, where W is a submanifold of the kth jet bundle, then the set of points, the set of parameters, such that the kth jet of JB is transverse to W is dense in B. And this is kind of an obvious thing, but we're actually going to use this next time. So not only you can look at the family at the parameter B, but you can also look at transversality in the jet space. So the kth jet of the function is another family of functions, but it's a family of functions onto the jet space. Okay, so that's it. So now I can state, well, I actually could have stated already, but let me state the transversality theorem that I guess is the main theorem of this part. That's called Thom transversality theorem. But before, let me stop again and ask if there are any questions about this lemma and this corollary. Are there? No? Okay. So let xy be manifolds. And now let's pick a submanifold of the jet space. And let's write TW. This set of functions such that the kth jet of F is transverse to W. Then TW is a residual subset of C infinity of xy. So residual just means a countable intersection of open and dense sets. And because C infinity of xy is a bare subspace, a bare set, that means that this is going to be dense in particular. Moreover, if W is closed, then TW is open. Okay, this moreover, we already proved. That was an earlier proposition. But it's also something we're going to use in the proof of the theorem. That's why we proved it earlier. Okay? Because we know a countable intersection of open and sets is always dense in a bare set, but it's not necessarily open. So we'll see examples where it's not open if W is not closed. It's not necessarily open, but it's dense because of the bare condition. Okay. And there's another theorem, or I guess a corollary to the proof. I'm gonna write corollary, but it's really a corollary to the proof. So you can't see it as a, it's just or you can think of it as a moreover, another moreover. So it's the following thing. So let's say that you have manifolds, and you pick a certain function, and you have a submanifold. Such that alpha of W, the closure of alpha of W is contained in some open set. Then you can perturb your function. You can find another function such that JK hold on. Oh yeah. Okay, I get it. Yeah. So basically, if the set of the alpha of W is contained in U, that means sort of the source points of all the jets in W is inside of some U. So you can find a G, which is basically a perturbation of F, which where we can attain the transversality condition without changing the value of F outside of U. So where G is equal to F away from U. So basically, if your submanifold, it only attains certain. If this is your alpha and this is U, so if alpha of your submanifold is here, so you have some condition on the jet space, and when you look at the source, it's above some points, and you look at the closure of that set, and if that's containing some open set U, you can perturb F to attain that transversality, so that F is not changed outside of this open set. Okay, so you'll see. We'll see how to do it next time when we show how this perturbation is done. Yeah, I mean, this perturbation is very, very plentiful. Like you can perturb it a lot. Like you can find the set of perturbations to be a countable intersection of open and dense sets. Okay. So one more corollary, and then we're going to stop. So I guess this is a real corollary, and this is a way that we use it. This is one way that we use the Thom transversality theorem a lot, which is just for zero jets. So maybe this is the usual or the more mundane transversality theorem. Is the following. So let X and Y be manifolds, and W is just a submanifold of the domain of the target. Then the set of functions which are transverse to W is dense in C infinity. Moreover, if W is closed, then TW is open. Okay, so maybe this, if you ask people who haven't taken this particular differential topology class, they might think about this as the main transversality theorem. So you just, you look at the set of functions that are transverse to a submanifold of the target, and that set is this. So notice that this is just the version of the Thom transversality theorem for zero jets. So the Thom transversality theorem holds in much more generality, and there are many interesting applications where if you can bear all this this theory that we defined with k jets and everything, and you understand the Thom transversality theorem, then almost any transversality thing that you want is a one-line proof. But if you just know this corollary, then it might be harder to prove other things that involve higher derivatives. So this, that's why I think it's really worth talking about Thom transversality theorem. But if you forget, this corollary is good enough for a lot of what you have in mind, like basically perturbing manifolds so that the intersection is transverse. Okay, this corollary A is enough. And the corollary B is basically doing the same thing, but without changing the function on some set. So let me write it like this. So let U1 and U2 be open sets such that the closure of U1 is contained in U2. And let f be a smooth function from x to y. And let's say that you have an open set containing V in C infinity. So this is kind of the density condition, but with some support, fixed support. Then there exists a G in C infinity such that G equals F in U1 and G intersects W transversely outside of U2. So, if you have this U1 and U2, for any open set near F, so as close to F as you want, you can find another G which is equal to F here and which is transverse to W out here. Okay, and if you think hard, this is a corollary of this other corollary here, again in the case where k equals 0. Okay, so I think that we can finish this class now, and then tomorrow we're going to continue and we're going to prove Thom's transversality theorem. Okay. Okay. Any questions? I just finished the recording. Or comments. Alguma pergunta? Comentário? Não? Então tá, pessoal. Eu vou gravar e eu não sei se eles vão colocar no YouTube agora mesmo, eu espero que coloquem rápido, para vocês poderem ver alguma coisa, algum detalhe. Eu não sei se dá para colocar no Google Classroom, eu acho que não dá. Então eu vou deixar assim mesmo. A gente vai ver como é que vai ser. Eu acho que é meio maratona, né? Hoje, amanhã e 4 horas da manhã é meio intenso. Mas bom, depois tem o resto da semana também para vocês ouvirem de novo. Mas, por favor, se vocês tiverem coisas que vocês não entenderam, se tiver alguns detalhes, me perguntem amanhã. A gente pode gastar um tempo falando sobre algumas coisas, que a gente está indo rápido no curso, então não precisa... Podem trazer perguntas para a aula mesmo, não precisa só para monitoria, não. Let me say this in English. So if there are things you don't understand, I know this is very technical, please, you can bring questions tomorrow. We're going to have a lot of time. I don't have to fill it up with lecture. We can discuss. You don't need to leave everything for the monitoria. Okay? So, all right.
O senhor pode botar as anotações também no Classroom?
Tá bom, vou botar.
Obrigado.
De nada. Ok, pessoal, então. Até amanhã. Amanhã, às 10 horas, a gente continua. Valeu.
Ok, gracias.
Tá bom.
Tchau,
Até amanhã.
tchau.
Chao.